Hello everyone, welcome back to our engineering mechanics dynamics class. In today's lecture we're gonna discuss dependent motion. If a particle its motion is dependent to another particle, how to deal with that, we'll see some theories on those. So our learning objective is formulate the position, velocity and acceleration relationship of two particles for dependent motion. So you see, for crane, we have pulley, where you have dependent motion of one object to another. If you have have a ride onto a tramway, you may see have pulley on both sides of the tramway that has a relative dependent motion with each other. And also on ship you will see a lot of this kind of pulley system that can be applied for dependent motion. So let's start. So first, assume dependent motion. Let us assume there is a slope. There's two blocks. One block is A, which is tied to a roller pulley here. So, and then another object is here, which is B. It just goes over there. So that's A. B. We can call the fixed point here, right, as O, or fixed point. So the distance from this datum, the fixed point, we can measure this distance from here to there. We can call it distance SA, and this distance we can call it SB. So what happens is, if this B goes downward, this A goes upward, where if the block B goes upward, then block A goes downward. It's opposite direction. So to find how to relate the dependent motion, let's start with what is common or fixed between these two objects, since they are tied with one rope here. So let's think, what is the length of this rope? So what is that? So if we take SA plus SB, and we can have another term, length P. So what I mean by length P is the length covered from here to there. So this point to this point, this length, curved length on the pulley, we can say length of the cord and pulley. So this length, and this length, which is the SB, is the total length of the rope. So LT. So this is fixed. No matter how much B moves downward or upward, A moves upward or downward, the LT is fixed. Now let's start from there. This is the one equation that we have. No matter what, this equation is always valid. Now if we take time derivative of this equation here, equation 1, if we take time derivative, what do we got? SA over dt plus dsb dt plus LP, derivative of LP dt and derivative of LT dt. Now we know this LT is fixed, is the total length of the rope, which is fixed, and LP, the connection, the curved connection here on the pulley is always fixed because the diameter of the pulley is always fixed. So this two derivative goes to 0, and if we write the derivatives in a displacement over time, which is velocity, so if we write in that form, we get VA plus VB. So velocity of A object and VB object is equals to 0. So which leads us VA plus VA equals to negative VB. What it tells us that if one goes downward, another goes upward, so the velocity is opposite direction. Because if we measure SB is positive in this direction, then A would be negative. So that's how, or vice versa. So that's how it's we got VA equals to negative VB. Simple case. Now if we take a second derivative, we will get the same thing. For acceleration A is equals to negative acceleration B. So these are the simple cases. We have defined the velocity relationship for this case here of the picture here. Velocity is opposite, acceleration is opposite, and the total length is this. Now let's move to a new concept, which is a little bit complex than this, which may have more pulleys. So now in previous one we had only one pulley. Now we'll see what if we have more than one pulley. So this is the ceiling, and from there's one pulley down here, and then the pulley goes upward. There is another pulley here, then it goes way down to another small pulley, from the base line, and the rope goes on this way to attached to a block A, for example. So this is the center line of the pulley. There's different way we can solve this problem. First, we need a datum or origin where we can find the distance of these pulleys. This is attached, it is hanging from the ceiling. This is also hanging from the ceiling. This pulley is holding a block B downward. So we need a datum point. There is 3 different way we can do this to find the same way we did it for the first option. So let's see how can we do that. Let's assume first is this line here is the datum. So this, all the distance will be measured from this point. So we are assuming this point or this line as our baseline. So the distance from this baseline to this pulley, we can say it's a SB, and distance from this datum to the rope here is H, and this distance of the block moving away is SA, and we need another datum, which is this point. So we're taking this point is datum for this direction translation of A, which is SA, and from this datum is B. So if we take that, we see that this length from here is always fixed. This length of the rope is always fixed because the pulley only can go up this to this point. This pulley, this length is always fixed. Since the pulley diameter is fixed, this length is fixed too. This length of the rope is fixed too, and also same here. The length of the rope touching the pulley here is fixed. It's simpler if we avoid that length, then we'll be only left with this vertical length here, from here to here, here to here, which is same tangent from here to this point, and this length, this and this length. So these are the straight line length, and it will be easier to solve problems. So if we consider that, so the total length of the total length of the rope is twice SB, because this length is the same here, so twice, once and twice, so twice SB plus H, this length from here to all the way down, this is H, plus this length here, this length is SA. So this is the total length of the wire. We can say this is L. So this is one equation. So if we take the same way, take derivative of this equation, we will get this, since this is constant and this is constant, because H doesn't change, because this pulley is fixed and this pulley is fixed, so the H doesn't change. So what that gives us, twice VB equals to twice VB plus VA equals to 0. That gives us twice VB equals to negative VA. And if we do it for velocity, we can also take a second derivative, and we'll get it twice AB equals to negative acceleration A. I need to change that to capital A. So we got one for velocity and one for acceleration, if we assume this point as datum. Now let's see if there's any other way we can solve this problem. Again, I have to draw this. I have my one, there's another pulley here, and so I will have the rope coming here, going upward going upward, another pulley, and goes downward, touches another pulley and goes to the block which is on the floor. This pulley is attached here, and this pulley is attached from here, and then this pulley is holding a block B, and this is A. Now, the question comes, can we assume another point as a datum that we did for the first time? Can we, for example, take this ceiling, right, as a datum? So this ceiling is a datum. Is it different? Because first we assumed this point as a datum. Now we're going to take the ceiling as a datum, and what will happen? If we do that, same scenario, we will have this length defined by, for example, SA or SB. So if it's SB, we need to minus the length, because this length is equals to this length equals to that length, and we're neglecting this part, so we need to minus this part. We need to minus this length here. Let's assume that's X. So we will get twice SB minus X. So we got this length twice, and we can have this length also fixed, which is H. So plus H plus SA. Since the datum is here, so we have to assume the H is from here to here, so that's H. We have to take plus H minus X, so that is this length. So total length is H from here, and this length is X from here. So H minus X plus SA, and that is the total length L. If we take derivative, so this constant goes off. Again, we will have 2 VB plus VA equals to 0. It's the same equation that we had before, that leads us twice A acceleration of A, twice acceleration of B equals to acceleration of A. Same as we derived in previous slide. So no matter what, where we assume the datum, it will be the same. So this is the second datum option. We had the first datum, and then this is the second, and we can also have another datum taken at a different position. So again, we have the pulley, bigger pulley goes down, a smaller pulley goes to a block, the floor, pulley hanging from there, weight of a block B, and then this is block A. So what if this pulley is attached to the floor? What if we take a different point as a datum now? So what if we take this point, a fixed point? So what we can take as a datum? We cannot take a point, for example, this pulley point as a datum. We can't, because we can't do that, because this pulley is moving upward or downward. We need a pulley that is fixed. So either this one that we already take, or this position we already take, that is datum, or we left with is this point, because this pulley is also fixed. So let me erase some of the part. Okay, so now this time we're going to take this point as a datum. So in this case, we will have SB. The position of the pulley B is from the datum is SB. The length from this pulley to the fixed pulley here will be fixed H, because this pulley is fixed, this pulley is fixed, the distance here is always SA. We also had the same thing here. This distance was SA in the previous slide. So this is our third datum assumption. All this is to show you that if we can take any fixed point as datum, and that will lead us to the same solution. So if we take that as SBH, so again it comes this length from here is fixed and constant, so we're neglecting that. We're neglecting this circle, and then we're neglecting this part, and then we're also neglecting from this curve. So again we'll get, so this length from here to here, right, will be H minus SB, and this is two of those, this point and this point, here to here, so twice of those, plus H, this is this length of the rope, plus this part of the rope from here to here, so here to here, which is SA. Again, this is the total length of the rope. If we take derivative, that will lead us to since these are constant, that will lead us again VB equals to negative VA. Again, this will give us acceleration twice AB equals to negative this will give us 2 this will be negative here, so twice AB equals 2 acceleration negative A. So things to be noticed is that this is negative, and if I take this one on the other side, this becomes negative, so negative cancel out, it becomes positive for both cases. So the question comes, why VB equals to VA in this case, and twice AB equals to AA, while the previous one we had negative, because this is positive, so this goes negative, and then the previous one we had velocity opposite to each other, but this one we had positive sign. So why is that? This is because when this SA increases from here to there, so A moves this way, the pulley goes upward, the SB increases also. So when SA increases, SB distance also increases. So that's why they have the same sign, positive. Both of them are positive. If we go back to the previous one, we'll see when SA increases, the SB from here, right, from here goes upward, meaning the SB from the top reduces from the previous position. So SB is reducing while SA is increasing. and that's why they have a negative sign, opposite sign from each other. And also for the first data, is this case is also the same. When SA increases, SB from if it goes this way, the B goes upward, so SB from the top from here goes, for example, if it's in this position, then it will have a lower SB. So SB is also in negative direction, and that's why they have opposite sign. And for this one, we have a positive sign. So these things needs to be considered when we apply this concept in the problem. It's not always that all the velocity are same sign or opposite sign. It depends where you assume your datum, and we have to careful about those. So next we're going to solve some problems to clarify this concept that we have just studied. In next video we'll also solve some problem. Till then, thank you, see you.